Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. It's great to be back with all of you.
Hey everyone, glad to be here again too. Always exciting to see what new stuff is bubbling up in the AI world.
Yeah, and hoping we can cut through some of the hype and get into the actual science. It feels like there's so much noise sometimes.
Absolutely looking forward to another deep dive. It's crucial we stay grounded and critical while exploring these rapidly changing fields.
So, I was reading a really interesting paper recently about some new breakthroughs in using neuromorphic chips to simulate more realistic brain activity. They're finally starting to get past some of the limitations we've had with traditional architectures when it comes to simulating neural networks. This is something I've been banging the drum about for a while. We need to move beyond just software simulations and start building hardware that reflects the actual functioning of the brain.
Oh yeah, I saw something on that. Wasn't that chip that was demonstrating pretty good performance on image recognition tasks, even beating some regular GPUs in terms of energy efficiency? I mean, that's definitely interesting. But to me, it seems like we're already making huge strides with deep learning, even on traditional hardware. The scaling up of these massive models, like just the sheer data we can throw at them, IT quote S, unlocking a whole new level of performance that I'm not sure we should just discount, right? It's less about mimicking the brain's actual architecture, maybe, and more about brute force computation, finding the optimal representations with that data.
I'm still a bit skeptical that brute force is the way. I mean, yes, we can get good at recognition. Yes, we can generate some impressive text, but does it really understand, Like the reasoning and abstraction, that's where I see the limits. I saw another article on how these huge language models basically just regurgitate the patterns in their training data without having true conceptual understanding and ability to generalize beyond the known. It still seems to me that we are missing a huge piece of the puzzle. That's where I think a neuro-symbolic approach makes more sense, incorporating symbolic reasoning with neural networks to get real conceptual understanding, not just correlations in the data.
I agree with the limitations on current models and the importance of true understanding, but I suspect it's not just about symbolic reasoning or neuro-symbolic. I mean, maybe that helps, but it's deeper than that. I read an amazing piece that argued that one of the core things these models are missing is the ability to represent information in multiple coordinate frames and translate between them fluently. Current deep learning is great at finding correlations in a particular coordinate system, but that's not how the real world works. We naturally change perspectives, move around, shift our attention, and our brains are constantly remapping perceptual information into different frames to build a comprehensive understanding of the world. That's the sort of spatiotemporal understanding that I think we need to be thinking about if we ever hope to get to AGI.
That's a really interesting point about the coordinate frames. I think that ties in nicely with the idea of grounding AI, which has always been a problem. We train these models on text or images in a very fixed way, and they don't have a physical body to contextualize it all. A lot of the neuromorphic hardware that I've been looking at is actually incorporating sensors and actuators, trying to build what we call embodied agents. This allows the system to learn by physically interacting with its environment. It's about bringing in these sensory-motor loops, just like we have, so that it's not just processing data in the abstract, but relating everything to the system's own spatial awareness. And it's not just vision, tactile information, auditory, vestibular, everything is all integrated, and it's how we build a dynamic internal model of the world.
But isn't that just more data, more complex data, sure, with sensory input and all? I see where you were going, the real-world interaction, but I wonder if, instead of completely re-architecting everything, just scaling the current model architectures with these more diverse inputs, perhaps multimodal data, and a lot more compute. I mean, these models are surprisingly good at generalizing to tasks they weren't explicitly trained on, which points to some level of underlying representation. And those transformers, they're constantly evolving, and we're finding new techniques to make them more efficient and better at handling different types of information. I think that's the most promising approach we have right now. Remember the DeepMind Flamingo model? It can understand images, video, and text and translate between them. It's showing the power of these multimodal approaches. The more data and diverse data, the better these models get.
Yes, and they can do impressive things, that's for sure, but I think the understanding part is still just a clever illusion. I always come back to the symbolic representation, the ability to manipulate symbols, build conceptual hierarchies, plan and reason with that knowledge. That's what we need, and that's what these neural nets, even with all the data in the world, seem to be struggling with. I mean, the multimodal data is great and useful, but it is still just that data. It needs to be represented at a higher level, something along the lines of the old school symbolic AI techniques combined with the strengths of the neural networks. Take, for instance, the concept of a cup. It is not just about pixel pattern or a sound wave, but rather a functional concept, an object that can hold liquid, this symbolic functional reasoning that is still missing.
And I think that symbolic part is, again, a way of us imposing the coordinate frame on the problem. We are using it ourselves, so it makes sense to us, but we might be missing the forest for the trees. I agree there is a real gap, but I don't think the answer is just slapping on symbolic AI on top of a neural net. It's about how the system internalizes the relationships between the sensory-motor information and how that information is constantly being updated and transformed. That's the key. It's how we understand the world, with constant updates and remappings of our internal model. There's a paper I read recently on rodent navigation in a complex maze. It's fascinating. You can see the specific neural cells firing as the rat changes direction or gets to a familiar point, suggesting different coordinate systems and a transformation between them. We need to build algorithms that do that, build that understanding of spatial and temporal relationships.
That navigation piece is actually a great example, and something the neuro-inspired approaches are trying to tackle. The idea of place cells, grid cells, and the sort of internal map in the hippocampus, and how that's translated into actual navigation. I mean, that's a great model of how spatial understanding could actually emerge. And it's not just about vision either. It's about proprioception, inertial information. It's all these sensor-motor inputs coming together. The thing is, I think the challenge is trying to translate these complex biological models into effective algorithms and hardware. It's not trivial, and sometimes there's a trade-off. Do we strive for biological realism, or do we just look for what works? That's the balancing act. And I do believe there is incredible potential if we can crack it.
Yeah, and I think we need to recognize that the human brain is very specialized hardware, evolved over millions of years in a specific environment. It's incredibly efficient at specific things, but it's not necessarily the optimal general intelligence architecture that exists. Maybe the general principles are there, but trying to replicate it exactly is just chasing a biological implementation detail. We are already demonstrating that it is possible to achieve comparable cognitive performance by taking these principles, but without doing a literal copy of the human brain. Look at the success of generative AI. They are creating beautiful art, writing compelling articles, and even creating code just by finding the patterns in the data. It doesn't have the spatiotemporal or symbolic understanding that is being debated, but it is doing things that we previously considered to be only in the realm of human intelligence, all by brute force pattern matching and statistics. We might be on the verge of something far greater than trying to replicate the human brain. Maybe there's a more generalizable solution that doesn't involve mirroring the human system completely. Maybe that data, the diverse data, is the answer.
But the issue is, this pattern matching doesn't lead to true understanding. Yes, generative models can write text that looks coherent, but they don't know what they're saying. They can create beautiful art, but don't comprehend the underlying concepts that those images represent, beyond the training data. They lack the sort of higher-level abstraction. It's like a parrot that has memorized words without knowing their meaning. And that's why I think we need to go back to symbolic AI. I don't mean a full symbolic approach from the 80s, I mean the hybrid approaches, where you try to combine the statistical power of neural nets with the explicit reasoning and conceptual understanding of symbolic AI. Perhaps the use of knowledge graphs and neuro-symbolic algorithms that can manipulate these graphs, make inferences, make connections, and generalize across tasks, not just regurgitate patterns from the training data.
And yes, I think we've been here before. We were chasing symbolic AI in the 80s and it failed, right? It feels like this might be a similar trap we are setting ourselves. I think we are overcomplicating things by putting symbolic processing on top of the pattern matching of the neural networks. I think it's the coordinate transformations, the spatiotemporal understanding that we have to crack. The ability to build consistent internal models of the world based on the sensor-motor information that we are constantly receiving and transforming is the real key to general intelligence. And yes, the neural networks are good at finding the patterns, but only within the given coordinate frame of training data. We've made the mistake of assuming that the data is the world when it is just data represented in a way that we understand, but not necessarily how the world is, if that makes sense.
Yeah, I think you're all pointing to different aspects of a very complex problem. But to me, I think the idea of embodied cognition is crucial. These systems need a body, they need to be grounded in the physical world and not just be some abstract software processing data. I think that's the only way we can bridge the gap between statistical learning and actual understanding. When you actually start to interact with the world and build that sensor-motor experience, it is very hard to just see it as more data. It is a completely different paradigm of how you learn. And I think the advantage of neuromorphic hardware is that they are starting to incorporate all of that.
That makes sense. I'm just worried that by focusing too much on biological plausibility, we might miss out on some potential shortcuts or different solutions that might lead us to AGI. It's like trying to recreate a bird's wings when we can just build a plane. And yes, maybe we are not going to learn to fly by just doing brute force. I get it. But just the sheer scale of data available now and the advances in model architectures, it's still moving way faster than any of the other approaches. And perhaps it's just a matter of time. I mean, Just the advancements we've seen in the last year, it's crazy. Look at the models we have today compared to 5 years ago. It's exponential improvements. I don't see the current models failing at the general intelligence problem as long as we keep scaling.
But even if we scale to an unimaginable level, if the core architecture is just a statistical pattern matcher, we will still be hitting a wall. The scaling will not give us the understanding or reasoning that we are looking for. We need those explicit representations, the ability to manipulate knowledge, to reason about it. It's like we're trying to build a skyscraper with just mud bricks, and the higher we go, the more unstable it becomes. I mean, we've seen these models fail spectacularly in scenarios outside of their training data. That indicates a lack of true understanding or extrapolation, which will not be resolved by throwing more mud bricks at it. We need to change the fundamental design of the bricks themselves, or in other words, add symbolic reasoning to the mix.
I think the problem is not with the bricks themselves, but rather how they are arranged in a space and how the arrangement can be moved around, reconfigured, and remapped. We are looking for the wrong things. If our systems don't understand how objects and concepts transform through space and time, and that those different transformations are still representations of the same thing, they will never be able to achieve true understanding. Take a car. If you see a car from different angles, it is still a car, and you know this despite having different sensory input. The human brain does a transformation between the different coordinate system, or it might maintain different coordinate systems simultaneously. That's something we need to explore. It is the ability to translate between the different perspectives that is missing.
So, it seems like we have a few different paths we could take. But if we're trying to build truly intelligent systems, I think we should start by looking at how biological brains actually achieve intelligence and how we can move from the data level towards those higher level representations, using hardware that more closely mimics the brain's own structure and sensor-motor interaction.
Yes, and I think we should also acknowledge the incredible progress we've made with purely statistical methods and keep pushing the limits of the current model, architectures, data, and compute. It's important to keep exploring, and we can't really discard something that might take us to the goal and might do it faster. We can also try to integrate some of those sensor-motor loops and multimodal data streams into these models to see what happens.
And for me, I think the key is to go back to symbolic reasoning and representation, combined with the powerful learning capabilities of neural networks, but with the focus on explicit representation of knowledge and the ability to manipulate that knowledge. I feel this is still the path that is more aligned with actual conceptual understanding and generalization.
And for me, it's about those spatiotemporal transformations and building algorithms that can translate between coordinate systems and not focus on the static data or symbolic representations only. The dynamic understanding of the world that we possess is not a fixed representation, but rather a constantly updating and remapping of the world around us. That's the real key. We have to stop looking at static data sets and focus on the dynamics of the data and how we internalize that. That's the path I think we should explore further.
Okay, so it sounds like we have some very different viewpoints, but we all agree that building AGI is an extremely complex challenge that will require us to push the boundaries of what we currently know. But it's clear there is still a lot of research to be done. From my perspective, I'd like to see more research on neuromorphic computing, and particularly how to incorporate embodied cognition into these systems, sensor-motor loops, and more efficient ways to do backpropagation and learn using sparse coding.
And I think we really need to keep pushing the limits of deep learning, experimenting with novel architectures, multimodal datasets, and perhaps the inclusion of some of the sensor-motor information into these models, but with the primary goal being the scaling and finding the patterns. So, scaling new transformer architectures and incorporating sensor-motor streams into it.
For me, I think it's critical to focus on neuro-symbolic approaches. We need to really nail down how to integrate symbolic representation with neural networks and to create algorithms that can reason with knowledge and not just learn patterns. We should explore novel knowledge representation formats and combine them with the learning capacity of neural networks. Something along the lines of the old AI systems, but with the neural network layer and with the knowledge graph.
And from my point of view, we need to build algorithms that can understand and translate between different coordinate representations, with spatiotemporal understanding being the key. We need to explore new mathematical frameworks and neural architectures to accomplish that. We need more research in the neurosciences about how the brain does the mapping and coordinate transformations. It also calls for new types of experimental frameworks, not just fixed data sets.
Right, so a lot of interesting avenues there, and it's exciting to see the breadth of research happening. I think it is important to approach the general intelligence problem from different perspectives. That's how we will get somewhere in the end. Thank you all for the great discussion.
Yeah, great discussion. Definitely agree there is still a lot to be explored. See you all next time.
Always good to get some different perspectives and cut through the hype. Looking forward to the next one.
Indeed, another great discussion and many paths to explore. Catch you all next time.